Assalamu alaikum. Welcome to lecture 7 on electric circuit analysis 2. Um, I'm Dr. Khuram Naveed and I'm going to deliver this lecture on AC power analysis. So, so in this part of the lecture, we are going to understand how a sinusoidal source is delivering power to a passive linear network or a circuit that is composed of passive elements. So power is a function of V multiplied by I. So in case of continuous voltage and continuous current, we have a continuous power that is equal to V of t into I of t. So so therefore, power is also an oscillating phenomena. Therefore, one thing is very clear that the power is going to be different at different instants of time. So if you are going to measure time at power at this point in time, you will get maybe maximum power. But when you measure power here, you will get zero power. And when you get measure power at this point, you will maybe get a value that will be between maximum and minimum. And similarly, if you measure power here, you will observe that power is negative. So, uh, so this uh, type of power is therefore referred to as instantaneous power. So, power that has different value at different instance of time, right? So, the term instantaneous is there to refer the continuity of the power function, right? So let's try to find out an expression for power in terms of sinusoids. So we have this voltage source, that is V of t, which is equal to this sinusoid, and we have another input source, that is current. Um, in fact, we have the same source representation of the voltage for that source, and this is the representation of the current for that source, right? Okay, so when we put these sinusoids in this expression, we will get this particular expression where we have this Vm Im at the outside, and then we have a multiplication of two cosine functions. So from this trigonometric identity, we can um, obtain a more meaningful representation of this multiplication of two cosines. So from this identity, we can write this cos A into cos B as 1 by 2 into cos A minus B plus cos A plus B. So first let's write this part. So you will realize that once you, uh, so this is your A, this omega t plus theta V is your argument A, and this omega t plus theta I is your argument I. So in this case, you will realize the omega t part will be cancelled because of the minus operation, and you will end up with theta V minus theta I. And in this case, the omega t part will be added. So omega t parts, omega t plus omega t will be added, and you will get 2 times the omega into the continuous variable t. And here you will see that theta v and theta I will also be added. So this will be your phase for this sinusoid, and this will be the angle argument. Uh, Rather, the continuous the argument that is responsible for oscillations of this sinusoid, right? Okay, um, so as you can see, the power. So this can be seen as a DC part or constant part of the instantaneous power, which is not oscillating. Instead, it is a number, because so this cos theta v minus theta I is a constant, but here, because of the presence of this continuous variable t, this is an oscillating function, and it is oscillating at twice the frequency of either the voltage source or the current source, right? So, and as that can also be seen from this diagram, where as you can see, instead of completing one cycle in time t, power is completing two cycles in time t. So this is Vm into 1 by 2 into Vm Im is the amplitude of the sinusoid that is oscillating here, and this is a DC part that um uh, is the value around which this sinusoid is going to oscillate. So this line, this dotted line, is the is the line, it denotes the this DC part, and the sinusoid that is oscillating around this uh, constant value, that is dotted line, is this part, right? Okay, so the problem with instantaneous power is that um, it is uh, it is inconclusive. It does not tell us exactly what is the power delivered by the source. That is because so this instantaneous power has different values at different instance of time. So if you measure, as I've already discussed, if you measure power at this point, the value of power will be negative, and it will be different to the if you measure the power at this point in time. But if you measure power here, it will be positive, and it will be a different value altogether. So it is this instantaneous power is not a conclusive um, way of um, describing the power delivered by the source to the circuit. So so therefore we evolve this concept further. So and so instead of computing the power at a certain instance, we decide that we should compute the power um, in an interval, and that interval is the time period of the input sources, which are current and voltage sources. So um, so we want to compute the power that has been delivered by the source V of t or I of t in one period, uh, right? So this is one period, 0 to t is one period, right? So in order to find the um, in order to find uh, the power delivered by the source in this particular interval, so we instead of addition, we will use the integration operation, right? Because of this is a continuous function. So once we do that, once we obtain the power delivered by the source in the interval from 0 to t, we can then divide this power with uh, the time the time period to obtain the average power, p, capital P, right? So so we have this power p of t. We calculated this here in this expression. So we take this expression and we put it here. So once we do that, so this integral will move inside, and it will and we will integrate this part, the part that is not oscillating, separately from the part that is oscillating. So since this part is all constants, so this it does not involve anything that is depending on t. So we can take this outside of the integral, and we will be left with this part inside uh, uh, this part inside the integral. And so once we integrate it, we will see that this is nothing but t. So this this integration of dt will culminate in capital T, and T will capital T will cancel this capital T, right? So we will have this part unchanged in case of this integration. But in case of this integration, it is very interesting to see this is this part will be zero. This part will completely cancel itself out, and that is because in this interval, if you look at it, you have it will have equal number of positive area at the positive on the positive side to the area that is on the negative side. So because the sign of the area on the positive side and the area on the negative side are different or opposite, so this area on the negative side will cancel the area that is on the positive side. So to understand this better, let me highlight this part which is starting from here. So once I highlight it from here till here, so this is again a cycle, a complete cycle, right? Because now it is starting at some point before time t is equal to 0, and it is ending at some point before this time capital T. Okay, so here, as you can see, this envelope will have same area that is uh, covered by this envelope, but both the sign of these areas are completely opposite. So this area will be positive, but this area will be negative. So this means this area will cancel this, the area covered by this curve, and the area covered by this positive envelope will cancel the area covered by this negative envelope, and therefore you will end up with zero area, and therefore this expression or this expression will contribute zero to this whole um, uh, expression, and therefore we will only remain with this part, that is the part that does not have an oscillating uh, function. So this is the average power that we have. So now the next challenge we have is to represent this average power in phasor domain. We uh, so in terms of, so we write phasor of voltage, and then we write the phasor of current, and we are writing this expression in this way because here we have 1 by 2, so we write 1 by 2. Here we have Vm and Im, but we as you can see, we do not have two cos functions. We have only one cos function that has uh, the phase of voltage minus the phase of current. So this, by writing it this way, we can uh, we can express this conjugate of the phasor I would mean the phase of the voltage, phase of the current is negative, because that is because the conjugate operation only changes the sign of the phase. When we expand this expression, we end up with this one. So we do not have this sign part here. So therefore, we can represent this by writing it as a real part of VI, right? So this is a phasor representation. This particular form is a phasor representation of this expression, right? So this is just to make sure that we find a way to um, to be able to represent this average power in phasor form, because in this course we'll be dealing with phasors. So a resistive load absorbs power at all times, while a reactive load, a load that contains a capacitor or an inductor absorbs zero average power, right? So to observe this, let us take this expression and for a resistive load. So where in a resistive load we have this phasor of voltage is equal to phasor of current into resistor, and we can write this uh, uh, as you can see here. That is because this I magnitude of phasor of I squared is obtained by this um, expression, and here as you could see, this is the phasor of I and this is a complex number. So let's say it is a plus jb, and this is the phasor or the conjugate of phasor of I. So a conjugate of phasor of I would be a minus jb. So when we multiply a plus jb with a minus jb, we will end up with a square uh, uh, plus b square, because the negative in the expression will be will be made positive when we take square of the j, that is j is equal to under root minus 1. So when we take square of j, it will contribute minus 1, so it will convert the negative of the formula to positive, and this will be equivalent to the magnitude squared of the phasor I. So therefore we this expression will be a real expression. It will not have any imaginary parts, and as you can see, this will culminate into I am squared into R. That is because this magnitude squared of phasor I is effectively equal to square of the amplitude of I. So as you can see from here, the resistive load will always absorb power, while we can also denote this power using this expression. But in case of reactive load, that is in case of inductor and capacitor, the voltage and current will always be out of phase, and that phase difference between voltage and current will be 90 degrees, either positive or negative. And when we put this positive or negative phase in this cos function, and since cos is an even function, it will convert the negative sign into positive, and it will always give you answer that is 0, and therefore this whole part will become 0. So reactive loads will absorb 0 average power. Right, so let's have a look at some of the examples. um, so we are given these two voltage sources, a voltage source and a current source. uh, so we need to find the instantaneous power and the average power. So we can find the instantaneous power by just going back a bit and using this expression. Uh, this expression. So in order to find the instantaneous power, we need to write uh, the multiplication of the cos functions of the current and voltage like this, and then we will be able to uh, find the um, instantaneous power. So 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 voltage sorry a power is equal to vi, and we multiply uh, the sources, both sources, and here as you can see the amplitudes will multiply with each other. So we have 1200 here, and the cosines will also be multiplied, but in the case of cosines we can use this identity to write them like the expression that I've just shown you before. So that way we will end up with this term that does not involve any um, a continue any function of t, and but here we will have a function, a cosine function that will be a function of t, and it will have twice the frequency that either of the voltage or current have. So so this is the instantaneous power. but when we compute the average power, we just use this part. So this part is the average power, and this will be actually 344.2 watts. And this is, as you can see, it is conclusive when we compare it with this one, and this does not seem like conclusive. So this part, when we multiply 600 with this part, is the average power, right? Okay, so now let's have a look at another example. So here we have to calculate the average power absorbed by an impedance Z when voltage V is given. So first we need to find the phasor of the current in order to find the power. So we can find the phasor of current by dividing the phasor of voltage with impedance. And since we are dealing with two complex numbers, we will end up with another complex number. And once we have I, that is phasor of current, we can multiply V, that is phasor of voltage, with phasor of current, and we can in fact we can use this average power expression because we want to find average power, right? So we can find this, we can use this expression that will require amplitude of the voltage, amplitude of current, and the phases of the current and voltage, and we will get this answer. So in this example,